our Windows shell emulation, and what we get at the end is this URL. So we have a command sequence, and we generate a URL from it simply by emulating all the echo calls and having an ftp.exe command file interpreter, and then we can generate a URL from it and then pass this one onto the download modules to actually download this FTP URL. What you see here is rather nice. We came across this using the ASN exploits, and what you see here, the actual payload, or in the top you see first an HTTP request and then a MIME encoded payload. So we had to also include our own MIME decoder, or base64, I guess it is, the algorithm used or similar. And then again, after MIME decoding, you see the command line at the top, what we did with the original hexdump. We could again generate a command sequence from it. It's using, so this is also a create process shellcode, and then turn this into a TFTP URL. So we have a lot of download modules for all these different kinds of URLs. And as you can see here, using the Windows shell is pretty common, but it's not only used with the create process API and shellcodes. The most poor thing most bots do is they take a public bind shell shellcode, so because most proof of concept shellcodes are bind shells or reverse shells, and they don't change the shellcode in the public exploit because that would be too professional. They cannot do that. They're too lame. So what they do is they take these default bind shell shellcodes and add code to their bot, which then connects into the shell and automatically sends the commands they want to it. So this is really cheap and poor, but it's the way it works for them. So usually you don't see just one exploit going over your network, but you see an exploit and then an automated shell connection, and they just retry for several times connecting into the shell before they drop that host, and then send some Windows commands via this bind shell list as well. No real black hat would do that, but most botnet herders are kiddies still today, even though media tells you, well, it's a lot of high capital behind botnets nowadays and whatever. So now we have that nice URL, and we can now somehow obtain the malware using our download modules. We had to implement our own HTTP and TFTP modules because we first stuck with curl because we were CURL, the library. We thought we were developing open source, so why don't rely on other open source software as well? The problem is the CURL library is RFC compliant, and bots or malware is not RFC compliant. That means we had to implement our own download modules, which, well, it looks like HTTP, but there's certain flaws in some malware, like they don't say, send a carriage return at the end of each line, but only a return or whatever. And this means we had to write a very, very friendly download module which accepts a lot of bullshit, and we had to add some tweaks. The same goes for FTP, because the FTP client, the ftp.exe in Windows, is also not RFC compliant. And then, because the FTP client in Windows is not RFC compliant, malware authors wrote their FTP servers not RFC compliant, so the Windows FTP client could load it from their servers, but then again we could not use CURL because URL was RFC compliant and it couldn't work with these intentionally broken FTP servers. And then of course there's a lot of, well, let's say proprietary download modules like csend and creceive, which were very famous in Agobot. This is not a real download protocol. You just connect to that port, send or receive the length of the file you want or are getting, and then the file is simply streamed over that connection, so nothing so sophisticated. And we have the very, very sexy download link module, which downloads the malware from linkbots, which is really nice because the linkbot download is three-staged. First of all, you have a shellcode. Then in the shellcode, the shellcode is automatically generated in runtime by the linkbot, and it generates a code that is then executed, which in turn generates a key. This key is used for authentication at the malware. So in order to download the malware, you have to see what key the shellcode generates, and then use this key for authentication at the actual exploiting host for being allowed to download. LinkBot appeared like, I don't know exactly, it appeared some month ago after the first Nepenthes release, so we were somehow tempted to assume this was a try to avoid Nepenthes, but we were able to write some even more generic patterns, so to speak, which could then, with some C code, also extract the keys from the shellcodes. And now a LinkBot URL at the end, for example, contains the base64 encoded key used to download the malware, which is generated in these shellcode steps. Yeah, that's it about the most nice servers. No. Well, as I've said, this is not my laptop, and it's coming back. Just a second, please. Yeah, by the way, if anybody saw it, it's a Seabase, a black bag with a yellow arrow on it. That's mine, and I would like to have it back. Yeah, I guess this computer is now turned off for whatever reason. Anybody familiar with Dell laptops? Ah, it's coming back. Huh? No, it has like 2 hours of battery remaining. Battery is critically low. Okay. Just try to give it some power. Well, yeah, there's a reason why I try to never present it on my own laptop. Well, if any of the heralds could help me, that would be nice. I've never used a Dell laptop before. Hast du mal hier Strom ansteckt?
It's still be useful if you combine it with I talked about earlier. You can get it to that null page. You might be able to do a lot of allocations page right after the page. So if you'd have a function pointer that's set to null, it would go to your null page, which has all these nulls with sure.
Yeah, it's resuming now.
The entire null page will just be not, right?
Yeah, I'm sorry, but it's coming back now.
And you'll have your shellcode in there, right? And so these things sometimes help in exploit null pointer references. There are constraints. Sometimes this is enough. Right. So the last piece of null pointer references. Some operating systems also map to a page by default, but they don't allow you to read it or write it.
Well, is there any special key combination I have to press to? Oh, there it is. Great. So here we go again. Yeah, these are the most sexy download modules we have there, and we can download nearly all malware with these download modules now. So the next step, of course, is then somehow handling the malware, because we're not like people collecting stamps. We don't collect malware just for fun. So the simple thing is for doing it like simple collection is write it to the hard disk, but we have some submission modules for submission into various databases, which is great for correlating data and whatever. There's a submission module which automatically extends the malware to the normal sandbox. You configure your email address in the submission module, and so you automatically get email to sandbox to run of this. Now CW Sandbox also has a public interface, and in cooperation with cwsandbox.org, there's also the same module also works with CW Sandbox. And there's the submit Gotek protocol, which submits a file via the Gotek protocol, which I'm going to come back later to. Yeah, in theory, we would now have an Nepenthes demo, but this is a Windows laptop, so unfortunately I cannot show you the software, but you have a screenshot there. So what you see is the log output, and what you can see up there is that there's several exploitation attempts using an already black hole DNS distribution server. So they were using a central server, ftp.peruvianpower.com, for spreading. But even at that time when we were running this test, the DNS was already black hole to that fictional IP address. So these runs failed. And as you see, it's the same with the limateam.com server. Yeah, and then there were some unknown shellcodes. We have, well, this is like only a probe whether the computer is vulnerable. As you can see, it was a 0-byte shellcode. Yeah, and then what you can also see there is that well, the timeouts were reached for these black hole hosts. And what is interesting there is also there was another computer, 84.60.251.5, which was like a normal home computer, which was infected, which was serving as a malware server. In that case, we often assume that this one was simply behind a normal personal home router. And, well, of course, these are using NAT, so we couldn't connect back to the spreading host to download the malware because we couldn't get through the home router's NAT. NAT, Network Address Translation, you're probably familiar with it. And yeah, that's it, what you can see on the screenshot. It's the same again down there. So sorry, no demo here. So what we have founded is now that the MW collect lines, well, you simply have a lot of MW collect sensors, which is now, of course, Nepenthes. The software is now called Nepenthes. And we have a central database. And I mean, the picture is not too interesting. But so we have now a database of over, I guess it was 27,000 different malware binaries collected through the last, it's not a year now. And we're sharing them with everybody for free because, you know, it's all in the spirit of open source. And if you want to get access to the binaries, you can just go to that URL down there and apply. Of course, we have some joint requirements. First of all, because we want our database to grow, you need to supply your own sensor for access. So everybody who contributes malware also gets all the other malware. And the second thing is you need to somehow prove some level of trust because, of course, we don't want to feed all these black hats with the malware. Yeah, that's it about the MW Collect Alliance. So if you have any questions to this, feel free to come to me afterwards. There's a lot of people already. I guess it's more than 100 sensors now distributed over the whole world. And yeah, we're also submitting all malware for free to all these antivirus vendors. So it's just doing a good thing on the internet, and it's not hard to set up an Nepenthes daemon, so it would be great if you could join us. Now to the second part. We have now, with some work, obtained our malware binary. And yeah, of course, as these are often packed and whatever, you cannot just run them through strings and then see some IRC command and control server information. But we need to analyze the collected binaries somehow. And this work, CW Sandbox, is written by Carsten Willems as part of his diploma thesis, hence the name CW. I guess it was at the university, I guess it was still Aachen, at the University of Aachen, but they now moved to Mannheim. Yeah. So what the sandbox does is an automatic behavior analysis of the malware. So we take a VMware or whatever VM, install Windows in it, install the sandbox software, and then tell the sandbox software to run the binary. It works similar to Norman Sandbox regarding the output, but the main difference is that Norman Sandbox has its own virtual machine included in the software, whereas you run CW Sandbox in an existing Windows virtual machine. And yeah, there's currently still a better version available, but they are also already selling it. So it's a commercial software, but most researchers get access for free. It's, I guess, available from Sunbolt. You can, but you see it's an .org domain. First, there's a free open web interface, so you only need to pay if you want it on your own site. If you can, if you don't have any privacy issues with running it at their sandboxes, you can get the results for free. And also, if you're a researcher, yeah, you can talk to Thorsten Holz. He's not today here anymore, but he was yesterday. Or just drop in an email. It's also on that page, and there shouldn't be any problems. So, how does it work? Yeah, how does Windows program work? You have just a normal Windows application at the top layer, which uses the Windows API, or perhaps if it does as it shouldn't, it also already calls the native API. And this Windows API is just some libraries providing some chain calls, either going directly to the kernel or via some other API going to the kernel. And there you have the user-made kernel mode barrier, which is going via interrupt or sysenter, depending on your CPU and Windows version. And then at the end, you somewhere land in the Windows kernel where your request actually gets processed. So as you probably know, Windows is a really monolithic kernel, so everything is running in kernel space, all the real stuff. So all you have in these Windows API is either simply Yeah, a wrapper, so the API is consistent between kernel versions, or does sometimes some pre-processing, like the new Windows XP and whatever kernels are all highly depending on Unicode. They're all using UTF-16, and if you have a normal ASCII command called, it's of course first converted to UTF-16 and then sent to the Windows kernel. So this is the way a normal Windows program works. Now, this is a simple example of code hooking.